Let's take a look at finding areas bound by polar curves. Now the formula that we're going to use is the integral, well, half times the integral of r squared with respect to theta. And I think the best way to do this is just to try an example. If you look at the first example, we've got r equals 3 minus 2 sine theta. Now don't forget, on polar coordinates, theta represents the angle and r represents the distance. It's just like a new way of representing our two-dimensional system, isn't it? Instead of how far you go across, how far you go up, we're saying the angle and how far out. We should be familiar by now with the fact that there is when theta equals 0 or 2 pi, and if we rotate round, as the angle increases, we move around in this direction. So the diagram's been given to us, but just to get a feel for where this comes from, like if you think about it, if I wanted to sketch this, when theta is equal to 0, sine of 0 is 0, so r would equal 3. So that's just telling me initially the r value is 3, and then as theta increases, and this line here would be when theta equals pi over 2. So if we sub pi over 2 in, sine becomes 1, and we get 3 minus 2 times 1, we get 3 minus 1. Let's try 3 minus 2, which is 1. And then over here, if we go to theta equals pi, sine of pi is 0 again. So we get 3. And down here, theta equals 3 pi over 2. Sine of 3 pi over 2 is minus 1, so we get 3 minus 2 times minus 1, which is why we get the greatest r value here of 5. Alright, so we're being asked to find the area enclosed by the curve. The curve is defined all the way around here, isn't it? So we can actually integrate from 0 to 2 pi. There is symmetry involved in this as well. Like if you've got a function of sine theta, it will always be symmetrical about this line here, where theta is pi over 2. So if you wanted to, we could integrate from pi over 2 around to 3 pi over 2, and just double the answer. One thing I should mention as well when we think about limits for these integrals, normally we think about integral limits being trapping the area this way if they're x limits. In polar, it's different. So what you've got to try and visualize, if I said theta was equal to 0 and theta is equal to pi over 2, what I would be doing there is that as the theta increases, you trap the area like this by radiating out. Okay, so obviously if we want to trap all of this area, we have to rotate round from 0 to 2 pi, and that will give us that area there. So it's very important that we use the right limits when we do this integral. Half r squared, so 3 minus 2 sine theta squared with respect to theta. Set up the integral, like you get your first mark for writing this down with the limits. Okay. So how are we going to integrate this? If we expand this out, we're going to get 9 minus 12 sine theta plus 4 sine squared theta. So we can integrate negative sine, goes anti-clockwise, back to positive cos. The main one that we have to be careful with is the sine squared. So if we use the double angle identity, 4 sine squared would be 2 minus 2 cos 2 theta. So if we integrate 9 with respect to theta, we get 9 theta. Minus 12 sine would become plus 12 cos theta, 4 sine squared, so that would be 2 theta, minus cos would go to minus sine. But don't forget, because it's cos 2 theta, we divide by 2. And then all we've got to do now is tidy up and sub our limits in, which are 2 pi and 0. Okay. So we've got 11 theta, so that'll be 11 lots of 2 pi. Cos of 2 pi is 1, minus cos of 2 pi. Sorry, 2 lots of 2 pi, so cos of 4 pi, which is still 1. Minus, when we sub 0 in, 0, 0. Cos of 0 is 1. Minus cos of 2 times 0, which is cos of 0, which is also 1. Okay, so just tidying this up, we would get 11 pi. 11, oh, right there, I'll tidy this up in a sec. Okay, so I was trying to do too much at once there. We've got, just tidying up inside the brackets, you've got 11 times by minus a half, and we've got 11 times by a half, so they would cancel, and I think we're actually just left with 11 pi. So the area bounded by that curve is 11 pi units squared. Example 2, we've got r equals 2 cos 3 theta between 0 and 2 pi, and it says find the area of one loop. Now the sketch is given to us on the diagram, but I'm going to just have a think about why the sketch looks like this, because that's going to help us with this topic. Okay, so if we're thinking about what the sketch would look like, we've got to think about, like, as theta goes between 0 and 2 pi, what happens to r. So a nice thing to do maybe is just to start by subbing in some values, like if theta is equal to 0, we know r would be equal to 2. If theta would be equal to pi over 2, we know r would be equal to 2 cos of 3 pi over 2. And cos of 3 pi over 2 would be 0, wouldn't it? Okay. So what we've got here is we've got a situation that didn't happen before in the previous one. Like if you look at the previous one, r was never 0, like the curve went all the way around. We always had the positive r value. But because of the cos function, and I'm actually going to draw, let's see if you can see the parallel here. I'm going to draw, if I had the function y equals 2 cos 3x, the graph would look like this. So because it's times by 2, it would go up to 2 and down to minus 2. And because there's a 3x, we get a stretch in the x scale factor of a third. In other words, we're going to get 3 cos graphs between 0 and 2 pi. So why am I drawing this? Because this is not what our polar curve looks like, okay? We're thinking about r equals 2 cos 3 theta. So these y values that I've drawn here represent the r values, the distances that we're about to draw for the new curve. And where we've got to be really careful is, look here, when y is negative, in other words, if I sub in a number somewhere in here and I get a negative answer out, we don't want a negative r value because r represents a distance. Okay, so essentially what happens is the curve doesn't exist for any of these values here. And a nice place to start with this is to just think about, well, when does r equal 0? Because when r is equal to 0, that's when, at these points here, that's when the curve is back at the origin or back at the pole. So if I sub r is equal to 0, I've got 2 cos 3 theta equals 0. Cos 3 theta equals 0. So 3 theta would equal pi over 2, 3 pi over 2. Add on 2 pi because we're going to need more values. 5 pi over 2. 7 pi over 2. We're looking for 1, 2, 3, 4, 5, 6 solutions. So 9 pi over 2. And 11 pi over 2. So the values for theta would be pi over 6. Pi over 2. 5 pi over 6. 7 pi over 6. 9 pi over 6, so 3 pi over 2. And 11 pi over 6. So these values here would be these values here. When the original, like y equals x, the Cartesian one, when that was equal to 0, that's when the r values are going to equal 0. Okay? And when r is negative, or when y is negative, we basically just don't draw the graph, like the curve does not exist here. So try and get the link with the diagram that we've just been given. Okay, so in the polar world, when theta is equal to 0, we know r is equal to 2, so we start at a distance of 2 away. Now as x increases, this is like as theta increases as we rotate around. When we get to this value, which is pi over 6, that's when we go into the pole. Because at theta equals pi over 6, if I sub pi over 6 into this equation, look what happens. It tells me that r is equal to 0, so at pi over 6 we know we're at the pole. Which is why it's nice to solve when r does equal 0, because you figure out when you're back at the pole. And this is going to be a limit for my integral. If I want to find the area of the curve, I'm going to integrate this. One of my limits has got to be pi over 6. Okay? Then between pi over 6 and pi over 2, which is here, the curve, the y values would be negative, but if I sub angles in here, the r values would be negative, so we basically just don't draw it. Like a negative r value, you might think it goes over this way, but you don't want to be drawing that. Okay, so we only draw it for positive r values. And then as we get to pi over 2, the curve exists again, doesn't it? So between pi over 2, which is here, and this value, which is 5 pi over 6, which would be about there, we do get a loop. It's really hard for me to draw around this whiteboard. So it sort of looks like this, doesn't it? And hopefully you get the idea. I'm going to just show you what the rest looks like. So then we get another loop in that interval. This should be symmetrical, like the maximum value that we go out to here would be 2. The maximum value we go out to here would also be 2. And then we get this loop here. Okay, so that's an idea, a brief idea about how to sketch it. We do have the graphical calculator. Let me just show you how to do it on the calculator as well. Okay, so if we change the type to r equals, and then we enter the equation, which is 2 cos 3 theta. Just going to make sure I'm in radians. Okay. Try zoom ortho. And we get the curve that looks like this, don't we? Okay. So you can also draw them on the graphical calculator, which may be useful. Just be careful because the axis is not like to scale. See that distance 1 there is more than that distance 1. It's slightly distorted, isn't it? But you can draw these on the graphical calculator as well, just by changing the type to r equals. So now that we've thought about the sketch, let's actually just get the area. You have to be really careful here when you think about your limits, right? If I want to find this loop here, I can't use 11 pi over 6 to pi over 6. It does not work like that. Like, if you want to go around this way, you'd need to have like an increasing value of theta. So you could use theta equals minus pi over 6. So you could go from minus pi over 6 through to 0 to pi over 6. That would work. Also thinking about the symmetry as well, you could go from 0 to pi over 6. Like, it's probably easier to sub-zero, and you could go from 0 to pi over 6 and just double the answer. I think that's what I'm going to do for this one. Because if I double that answer, the half will cancel as well. Okay. So I'm going to say the area is equal to 2 times a half the integral from 0 to pi over 6. R squared, which is 2 cos 3 theta squared with respect to theta. Don't forget to set the integral up like this because that's your first mark. Okay, so we're trying to integrate 4 cos squared 3 theta. Think about the double angle identity. I'm going to use x because there's a theta in the question. So cos 2x is equal to 2 cos squared x minus 1. So cos 2x plus 1 is equal to 2 cos squared x. We've got 4 cos squared. So 2 cos 2x plus 2 is 4 cos squared of x. Now obviously now we can think about the angle that we're working with. We've got 3 theta. So 4 cos squared 3 theta is 2 cos, double the angle, 6 theta plus 2. So that's what I'm going to integrate. Integrate cos, we'd get sine. So let's say this is equivalent to 2 cos 6 theta plus 2 d theta between 0 and pi over 6. So cos integrates the sine, divide by the 6 plus 2 theta pi over 6 and 0. Pi over 6, 6 theta, so pi plus 2 lots of pi over 6 minus, if we sub 0 in, sine of 0 is just 0, so that just becomes 0. Sine of pi is also 0, so we end up with pi over 3. And that, don't forget, that's the area of just one of the loops. So the total area would be 3 lots of that, wouldn't it? Okay. Thanks, guys.